decorum here. Welcome everyone. My name is Anurag Verma. I'm assistant professor in Department of Medicine in Translational Medicine and Human Genetics Division at Penn. Thank you all for joining for our 2025-26 Informatics Talk series. Before we get started, we have a few announcements. Next month, on May 7th, in collaboration with Clinical Futures, we will be hearing from Dr. David Kaelper. Dr. Kaelper is the Chief Health Informatics Officer of the Metro Health System and will be presenting on Epic Cosmos, a paradigm shifting tool for certain type of clinical research. We hope you all join us for that session as well. You can also, next slide, you can also conveniently text to receive continued medical education for this informatics talk. Please text DBHI, small I-26 to 215-274-0239. You will get a confirmation text. If successful, you can text this number anytime between now and the 15 minutes after this presentation to receive the credit. If this is your first time using Cloud CME, please follow the instruction posted in the chat. There will be a Q&A session at the end of the presentation. We ask that you use the hand raising feature to ask your question. Also, feel free to write your questions in the chat during the presentation, and I can bring them up at the end. We ask that you mute your microphones. You can turn on live captions by clicking on ellipses on the top of your screen, language and speech and live captions. Finally, I'm so proud to introduce my colleague today, who's today's speaker, Dr. Huang. Dr. Huang is an assistant professor of pathology and laboratory medicine with a secondary appointment in the Department of Biostatistics, Epidemiology, and Informatics at the University of Pennsylvania Perelman School of Medicine. After receiving a PhD in electrical and computer engineering from Purdue, he completed a postdoctoral training at Stanford University. Dr. Huang's research focuses on advancing AI and machine learning in medicine, including the development of vision language foundational models for pathology, pathologist AI collaboration, neurodegenerative diseases, as well as work on optimizing large language models. His work has been covered by the New York Times, Stanford Magazine, and Stanford Scope. Today, Dr. Huang will discuss the critical role of building an integrated ecosystem for medical imaging and demonstrate how AI can assist pathologists to enhance diagnostic accuracy and efficiency through multiple AI algorithm development effort. And without further ado, Dr. Huang.
Hello, thank you so much for your introduction, and thank you so much for hosting me. It is my honor to present our recent work at here. So my topic today is investing in the future of science through AI and digital pathology. My name is Huang, assistant professor at Pathology and Informatics at UPenn. So before we get started, I would like to briefly recap how the typical clinical workflow, especially for the cancer patient, are looking like. So subjects, after the screening, becoming a patient, will come through a doctor's decision, and surgeon will take the tissue of the biopsy, take the biopsy of the tissue, and send the biopsy to pathologist, and then pathologist will inspect carefully on the whole slide image and generate the report, pathologist report, sent back to the doctor for treatment recommendation. And the treatment will be applied to patient, and we will have follow-up visits. And now, as you can see, pathology is the medicine's ground truth. It is the pathology that gives you the clinical diagnosis. It is also the pathology enable us to understand more about the disease mechanisms and understand and pushing forward the scientific discovery. So when we talk about pathology is the medicine's ground truth, it is very important. And today, my topic will be largely covering the clinical diagnosis. And also, we're going to cover a little bit on the scientific discovery. But when we talk about it is very important, pathology is a central pillar of the healthcare. And each year we have over 20 million new cancer patients and over 9 million cancer deaths and 455 million slides generated in the US. The volume is huge. But the problem is that pathology diagnosis remain quite subjective, inconsistent, and poorly standardized. And back in 2017, Elmore et al. Published a paper in BMJ systematically assessed the pathologist's diagnosis consistency and intra-observer variability across a lot of different pathologists. And they found that one biopsy inspected by 36 pathologists can actually give you 18 different diagnosis answers. So this is a huge problem. And in fact, for melanoma, the overdiagnosis rate can as high as 49% in white men, and overdiagnosis rate for white women can be as high as 64%. Well, overdiagnosis rate is super high, but also the critical underdiagnosis rate is also very, very critical. And currently, the underdiagnosis rate for melanoma is as high as 13%. And so, in a nutshell, 12 million of patients are misdiagnosed each year. Or in another word, 1 in 20 adults receive an incorrect diagnosis. Well, here's a very interesting survey on the Twitter back in 2023. Someone posted online and asking pathologists, when you're making a diagnosis of malignancy, do you often include the use of the subjective gut feeling? Well, across over 500 votes, 40% of the time, people will thinking they will mostly use the subjective gut feeling. So this is a very common issue and highlighting the need and necessary of introducing a more innovative solution to helping us to deliver more consistent and accurate diagnosis, therefore improving our healthcare and public health. So what is the current practice? Well, when pathologists are making the diagnosis, generating the pathology report, the current practice is a biopsy will typically be inspected by 2 different pathologists, and they will reach the agreement. If they reach the agreement, then they are all good. If they not reach the agreement, they will typically consult senior pathologists or send out for another people for final review. And hopefully, with the AI advancement, we can potentially improve the practice. And in the future, pathologists with AI's recommendation will give a more accurate final call. That is our long-term goal, and that is what exactly our lab is pursuing this direction. So when we talk about this pathologist diagnosis challenge, we talk about a lot of misdiagnosis rate. The first diagnosis challenge I want to give you an example is focusing on the cell level identification. And that example is plasma cell. Plasma cell is the gold standard for chronic endometritis, and it is a major cause, and it's the reason for infertility or the failure of pregnancy. But the issue is that finding the plasma cell is extremely difficult and tedious. There are usually as low as only 10 out of 1 million plasma cells. As low as only 10 plasma cell out of 1 million cells in the entire whole cell image. So finding the plasma cell is just like finding a needle in a haystack. It's very, very laborious, very tedious. Pathologists, they often have to take a look into the whole cell image carefully up to 30 minutes. And the underdiagnosis rate is still very high. So our solution is to provide a ecosystem, a platform called Nuclei.io that can not only able to hosting the case and digital pathology slides, but also we have several human-in-the-loop AI tools to allowing us to visualize the whole cell image and take a look into the AI suggestion and letting the pathologist to gain insight from AI recommendation. And our AI solution is a single nucleus resolution. Later, we'll tell you how the single resolution is conducted. But on the right-hand side, we also provide interactive annotation to improve the AI model. And we also allows the real-time machine learning development, and pathologists, they can always share their developed model on our social network. So at the end, and at the same time, we also provide virtual flow cytometry and quantitative analysis, so you can get an insight on how many cells are being marked with what kind of feature is the most important features to distinguish those different cell types. So the process behind it is every single slide after digitally scanned, we perform the nuclei segmentation. After the nuclei segmentation, we calculated over 115 features, 50 features, including the color, cytoplasmic color, morphology, texture, orientation, shape, and spatial and deep learning features. And once we have that feature pre-calculated, we can invite pathologists to annotate those cells of their interest. By cropping a region and mark them all as, for example, tumor or plasma cell, the model will be able to learn based on those features and those example positive and negative data points. We will be able to build a very efficient XGBoost classifier to distinguish different classes. The beauty of the active learning with human in the loop is that whenever you flag out any potential false negative or false positive, you'll be able to you'll be able to tell that on the slide, and you can make the further corrections so the model will get improved over time. So back to the question of the plasma cell, we apply this strategy to 39 different cases and invite 11 pathologists to inspect these whole cell images. We provide a clickable gallery, so pathologists, they don't have to inspect every single pixel of the whole cell image, but rather they will just take a look into those most suspicious plasma cell on the right-hand side and click on every single cell in the gallery and confirm it on the main canvas. Upon finishing the inspection, pathologists are invited to provide answer. Is there any plasma cell exist? If yes, or you can answer yes or no. And do you also still want to request additional CD138 to confirm your finding? So we conducted this control study with and without AI recommendation, and we found that using AI can basically double the sensitivity of finding the plasma cell. So this is a huge improvement. Also, sort of like indicating without AI, the misdiagnosis rate for plasma cell is extremely high. And we also found that using AI can reduce 69% of uncertain diagnosis and 63% of additional CD138 requests, suggesting using AI to assist, not replacing pathologists, can make your diagnosis better. Additionally, because we recorded all the user session, we found that using AI can reduce 62% of your total time saving. It also indicating your diagnosis with AI can also become faster. So keep in mind that the plasma cell classifier was just annotated and trained by only 2 clinicians in 3 hours using nuclei. So the same strategy can also be applied to anything that you're interested in, any cell you are interested in, such as neutrophil, mitosis, atypical cell, melanocytes, and so forth. So when we proposed this nuclear IO human AI collaboration framework, we did not only conducted the experiment on the plasma cell detection, but we also further investigating whether this platform can helping us to flag out the lymph node metastasis in colorectal cancer. So we invited 8 pathologists to inspect 25 cases with a total of 137 slides and check whether there's a potential tumor metastasis in the lymph node. And we found that using AI to assist pathologists, we can improve the sensitivity and true positive of finding out those lymph node metastases, especially for the isolated tumor cell, because those isolated tumor cells are extremely tiny. And this is just an example of the isolated tumor cell. You can see just about 12 of the tumor cells. And without AI to highlight you the region of interest, it is nearly impossible for pathology to flag out that small region. So often the time people will miss it. But with the AI assistant, it will drag your attention and prompt you to zoom into that area to have additional inspection. So it is okay for AI to provide some false positive, but with the human's eyes and human AI collaboration, we'll be able to deliver more accurate diagnosis. So that's the power and the beauty of introducing AI to assist pathologists on cell level inspections. So when we are doing this experiment for not only the plasma cell, but also the lymph node metastasis, we actually, because we developed the platforms, we actually recorded entire user session, including when and how they zoom into the detailed region of interest. And we also found that using AI can save up to 33% of time on ruling out negative lymph nodes and save up to 29% of time on flagging out positive lymph node. And that time saving is especially significant when your magnification is higher, meaning that using AI, you probably don't have to zoom into the very detailed, nitty-gritty detail and carefully check on every single pixel. Using AI, you can make the accurate diagnosis in low power. So we covered the first diagnosis challenge, which is the cell level identification. The second diagnosis challenge we're going to introduce is the tissue level identification. So as we mentioned that tissue level differential diagnosis is the medicine's ground truth, especially for cancer. But however, even the senior pathologists often disagree with each other. And even wet pathologists often disagree with themselves in different time. So, and that's the reason often the time when they're making a diagnosis, they not only have to educate it by more senior people, but also they need to frequently check online resources and textbooks to understand what's going on.
You sounded like
I
she
have
was.
massive GI issues. And I would
Yeah.
never walk into.
Um, oh, any questions?
Yeah, I think somebody was
Okay,
mistakenly
all right.
unmuted. I
Yeah,
muted
yeah,
them.
no problem. Okay, so let's move on. So now the question is, can we develop a powerful foundation model for slide level analysis and retrieval? So with the potential of improving our computational pathology analysis as well as improving the diagnosis as well. So the solution is to develop a vision language pathology foundation model for not only retrieval, but also knowledge query and image analysis. But every time when we talk about machine learning needs data, right? ImageNet is established over 10 millions of images with text. But in pathology, the problem becomes more difficult because there are more than 8,000 different disease types, but with only limited data with label in natural language. Part of the reason is microscopy data is much more complex. The other reason is expert annotation for pathology is extremely expensive and not going to be scalable. But at the same time, we also realize that a lot of people, a lot of board certified pathologists share their useful educational resources online through medical Twitter and on the other online forums. And every time when they share the example cases with canonical images, they describe the image carefully with a very detailed natural language description. And we realize that using such data, we may be able to train a very powerful vision language foundation model. And this idea is even before the ChatGPT. So by way of doing that, we collected 16 years of knowledge from medical Twitter all the way from 2006 to 2022. And in total, we get 208,000 high-quality image text pairs across 32 different pathology subspecialties or 32 different hashtags. By the time we established this data set, it was the largest public pathology vision language data set. So then we fit the text into a very simple OpenAI clip model text encoder and the image, the pair image into the image encoder, which is a vision transformer, and use contrastive learning to learn the association between the paired image and text and unpaired image and text. So the contrastive learning, the beauty of it is to, by doing the optimization, we will impose a higher cosine similarity on the diagonal on the pair image and text and reduce the similarity of the diagonal. So the model will eventually learn the right association between the pair image and text. By way of doing that, we eventually roll out our model called PLIP, or Pathology Language Image Retraining Model. So PLIP is a foundation model for pathology. It can perform a lot of different very cool downstream tasks. For example, PLIP can perform zero-shot classification. The point is that when you have an image and you encode that through the image encoder, you can also input a bunch of text candidates and feed into the text encoder and give you the text embedding. So basically, you just need to compare the cosine similarity between your target input image with all the different text candidates. And the one with the highest cosine similarity should be the one of your answer. And this is a H&E image of tumor. So that is a zero-shot classification. So we conducted experiments on 4 different external validation datasets, suggesting that the PLIP model is much better than the CLIP baseline. And it is the first time to show that using the crowdsourced internet data can actually train a powerful medical image analysis model. And this is a confusion matrix, also suggesting that the model is actually predicting pretty well on the colorectal adenocarcinoma epithelium and lymphocytes and smooth muscle, although the model gets very challenging on distinguishing mucus and the cancer-associated stroma. And the UMAP plot showing that the image encoder are able to capture the differences between the pathology concepts and is able to distinguish them into a very separate manner through the latent space representation visualization. But oftentimes, the zero-shot performance is not perfect. If we further want to improve the classification accuracy, we want to further improve the linear classifier on top of the image encoder. So we conducted linear probing experiment, and we found that by only fine-tuning the linear classifier, it can be very efficient within 1 minute. And our plot model is much better than the other competitors. And if we further want to improve the model performances, we can not only just fine-tuning the linear classifier, but also fine-tuning the entire image encoder. Then it will give us a better performance, of course. And the beauty of the foundation model trained on all different kind of pathology images is that here you can see, given the same model architecture, if you pre-train on pathology images, which is PLIP, and given the same amount of training data, you will have a much higher weighted F1 score or accuracy compared to the same model architecture, but pre-trained on industrial images. And so that's the powerfulness and the value of introducing foundation model in pathology. Foundation model cannot solve all the problem. When you are trying to solve a specific task problem, you can definitely fine-tune your model on your own data set. But it is better to fine-tune it on a foundation model in pathology rather than fine-tune your model from a ImageNet model. So that's a basic concept. So foundation model PLIP can also do text-to-image retrieval. For example, if your input text is normal colorectal cancer mucosa in H&E, and we will compare your text embedding to all the image embedding in our database. And then we will evaluate the one with the highest cosine similarity will be the right image to retrieve. So we evaluate this image retrieval accuracy by the recall at top K, meaning the proportion of the target image retrieved within the top K results. So we found that PLIP is much better than CLIP and random retrieval. And keep in mind, this is a pretty challenging task. So the performance is not as high as we are willing to see, but compared to the baseline is much better. And here's an example. If you're asking like breast tumor surrounded by fat, it will retrieve the right image that precisely matching your description. And lastly, another very important feature is image-to-image retrieval. If you input the image encoded into a vector representation, you can retrieve the similar image in our candidate pool. This is extremely useful for searching similar cases for education and second opinion. And because we mentioned that pathology, they always want to compare their cases to those canonical cases online or on the textbook. And this image-to-image retrieval is a perfect use case for such kind of practice. And our image-to-image retrieval is the best comparing to the model when we publish this paper. And it is very accurate on the class level retrieval for not only tissue type, but also organ type, and as well as the staining styles. So here's an example. If you input an image feature with a lot of mitotic figure, the most relevant image also features with those mitosis at the center of the image. So the conclusion is that PLIP is a foundation model for pathology research and education. For research, we can do zero-shot classification and transfer learning. For education, we can do text-to-image retrieval and image-to-image retrieval. And PLIP has more than couple thousand of downloads at Hugging Face, and right now with over 900 citations. So when we talk about all those cool stuff in pathology foundation model, here's a limitation. When we introducing the patch level foundation model, it can definitely helping us to do the classification problem. But to enable the quantitative analysis, patch level foundation model is not enough. Oftentimes, we need to segment the object and perform the real quantitative analysis so we can know what exactly is in the tissue, right? So oftentimes, we need to segment it in the pathology image through a AI model. But to date, there's no such reliable pathology AI model that can potentially segment all different type of tissue, all different type of region of interest that we pathologists are often interested in. So we develop a interactive foundation model for pathology image segmentation, trying to solve this quantitative analysis problem. This project is started when I joined Penn, and we collected over 1.6 million of image, mask, and text pairs across 8 different organs and 93 different concepts. Comparing to the second largest data set for pixel level pathology segmentation annotation, Biomed Parse, our data set is much more enriched with all different type of potential data, tissue, and classes. So also it is a massive amount of effort. The data collection is actually take more than 1 year. So after such data collected, we feed this paired image and text into this vision language foundation model. We only fine tune the vision encoder and keep the text encoder frozen. And once we encode the image into an embedding space, we will use the text vector to query the image and generate the final attention latent representation, and then use mask decoder to generate tumor area, stromal area, lymphocytes. And eventually, once we merge together, our prediction should be close to the ground truth in the training set. So that's how we train this interactive foundation model for pathology image segmentation. But when we talk about this, we talk about interactive. To what extent this is interactive? Well, if you see any imperfection in your initial prediction, you can definitely provide additional bounding box feedback, just like a segment anything model that Meta has introduced. So that bounding box will be used as a prompt, and we have a prompt encoder to prompt the embedding space, and that will helping you to change the prediction result in real time. And so that's the power of the introducing the interactive active learning to further helping us to improve the quality of the segmentation output. And comparing to the MedSam and Biomed parts, we found that VistaPass is consistently outperforms. And most importantly, VistaPass is fully functional in our platform TissueLab. So now you can just use a patch level classification with active learning to classify the patches that you are interested in. And those patches will immediately be used as a bounding box prompt to guide the VistaPass pixel level segmentation. After several steps, you will get very, very accurate segmentation result. And that is pretty much customizable, because every time when you do the patch level classification, you can select what kind of the prompt you want to do, and the segmentation result on the pixel level will be adapt to the things that you are interested in. So we talk about the foundation model. Foundation model is definitely very powerful, but foundation model can also do the classification problems, such as distinguishing making the diagnosis, distinguishing different disease subtypes. But in practice, it is usually difficult to achieve clinical level performances on a challenging diagnosis. One example is melanocytic neoplasm. Melanocytic neoplasm is kind of a subtype in skin cancer. It has 44 different subtypes with a very high over and under diagnosis rate and often misdiagnosis, as we covered earlier. Foundation model with zero-shot and few-shot performance definitely need further improvement. Here's an example. In melanocytic neoplasm, those subtypes are not flat. Those are forming the tree structure. So now our solution is, can we develop a knowledge-enhanced vision language framework to helping the model to navigate those knowledges and helping us to make a better diagnosis? In collaboration with the world leader in dermatopathology at UPenn, over the past 10 years, our collaborator has collected over 2,800 of carefully annotated image caption and knowledge pairs. After the data cleaning, we have come up with a dermatopathology de-identified collections. Every single concept, every single disease will pair with a knowledge, common knowledge or unique knowledge. For lentigo malignant melanoma, desmoplastic melanoma, every single disease will pair with representative image pair. And we will use those information to further improve our vision language foundation model. So the concept is that, first of all, we have to encode. So the training process is that the vision encoder will be frozen from the pathology foundation model, and we convert every single input image into vector representation and send to a mixture of an expert model. And then we will retrieve the most relevant images in our database and provide a fused image embedding, an enhanced image embedding for every single class. At the same time, we will also do a knowledge retrieval on the knowledge arm. We will compare our input image, to those knowledges processed by the text embedding, and then we will derive those enhance the knowledge vector, and we will do the knowledge enhanced contrastive learning to learn those 2,800 of image and text and knowledge pairs. And after the training process, once we have a new input image, we'll be able to tell you what is the potential subtype of this input image. Comparing to the foundation model, zero-shot foundation model, pathogen, conch, and mask, we found that MelanDX, our proposed MelanDX model, is not only better than the zero-shot prediction, but also better than the linear fine-tuned foundation model, or even fully fine-tuned foundation model, given the same amount of data. Partially the reason our MelanDX is much better is we are the first study to incorporate pathology knowledge into the model training process. So our model does not only handle the image and text, but also the knowledge description of every single disease. So the binary classification task distinguishing whether this is malignant or not can reach as high as 0.87 for accuracy. And for the 40-class differential diagnosis, situation can be quite challenging, especially we want to have a top 1 accuracy. And the baseline model for pathology foundation model can be very poor or even worse than the random majority vote. And linear fine-tuning and fully fine-tuning is still suboptimal, but our MelanDX can reach up to 70% accuracy. But let's rethink about the foundation model. Foundation model is powerful. Foundation model can do a lot of things. It can do retrieval, fine-tuning, image recognition, and segmentation. But even our best pathology foundation model, fine-tuned foundation model, MelanDX, fine-tuned on the state-of-the-art pathology foundation model, can only just retrieve 70% of top 1 accuracy across 40 classes. And the accuracies cannot even be used for as a AI assistance for pathologists. Think about the overdiagnosis rate in melanoma. It is 49% for men and 64% for white women. The issue seems like has never been able to solve. So how are we going to solve this problem? Will the foundation model still be the best solution? Well, that's the question. Well, I think the current foundation model is powerful, but the current foundation model also fails. It is definitely not the ultimate solution to solve all the potential tasks. Why the current AI foundation model fails? Well, my first hypothesis is AI is just learning the distribution, not evidence. For example, all the current foundation model trained on whole slide image and pathology label pairs. They may first train on self-supervised or contrasted learning manner on the patch level, and then aggregate the patch level into whole slide level through attention-based multiple instant learning, or through the through Titan or GigaPath approach, basically using the attention map to learn the global association on the histology image. But the problem is when you input the image and when you train your classification model to predict a different disease subtype, you don't know actually where those diagnosis features come from. You don't know that, and pathology foundation model doesn't know that as well. And secondly, how you're going to make that call. Diagnosis reasoning behind the conclusion is unclear. Well, you can argue that you can definitely use the heat map or attention heat map or gradient cam to highlight the region that model is paying attention to. But does that gradient map, those heat map, really reflecting the true diagnosis trajectory or reasoning behind the actual clinical practice? The answer is really, I would say the answer is no. And that's the reason why currently pathology, even the most powerful pathology foundation model trained on over 3 million of whole slide image, still worse than a human expert with only 5,000 whole slide image training. And the second reason is current training data is less informative, similarly as the first hypothesis. Right now, when we're training pathology foundation model, we input a whole slide image with a whole slide label or pathology report, and that report will tell you the tumor grade is the tumor grade is 2, tumor stage is 2, lymphovascular invasion is present, perineural invasion is present. But when we talk about lymphovascular invasion is present, where exactly those lymphovascular invasion are come from is unknown. And that's the reason when we train the foundation model from the image label pair, we're actually missing the critical reasoning, thinking, and trajectory to help the model align with our true human practice. So that is very problematic, and that's a huge problem. And that's the reason I think the current AI training is a misaligned with our human practice in clinic. And third is pathology high quality annotation is very expensive. When we talk about this reasoning and thinking and trajectory is missing, Well, we can definitely invite pathologists to help us annotate those data. But the issue is such high quality annotation is very expensive. We get 16 years of social knowledge to only curate 280,000 image text pairs. We invited pathologists with 10 years of collection to just give us 2,800 of image text knowledge pairs. Pathology annotation is very expensive, and there are only 220,000 expert pathologists in the US and Canada. So the data annotation is slow and inefficient and definitely cannot scale up. Not even mentioning pathology annotation may not always be the ground truth, as we mentioned about the consistent inaccurate diagnosis error. So our hypothesis is, what is our solution? If we think pathology foundation model does not solve all the problems, what is our solution? Well, my solution is, can we train from the behavior data? Can we train from the user behavior, the pathology diagnosis behavior, just like how medical students get educated by shadowing the senior pathologist? Well, think about the recent study. There's a very interesting study suggesting that using the imperfect human motion data, you can actually train an AI model to teach the humanoid robot to how to play tennis. That is super powerful, right? You don't have to feed the high quality data. You can just let the robot to learn imperfect human motion. You can still let the robot to learn how to do the things. So take such analogy, we actually have already collect such type of data. Remember when we conducted a nuclear IO user study with 8 pathologists when inspecting the colorectal lymph node metastasis, we actually recorded the entire user behavior log when they are making a diagnosis. Well, of course, this is after IRB approval. So every single pathologist, after 1 or 2 hours of behavior of inspection, we recorded the entire behavior, and eventually they will generate us over 100,000 lines of behavior log, including the mouse movement, keyboard activity, and zoom in, zoom out behavior. We have all those behavior, and we believe such behavior can actually be useful to train an AI model that does not require explicit pathology annotation. Well, actually, we did that. We learned the visual chain of thought agent from the expert whole line image diagnostic behavior. We get the raw data contains 25 cases, 137 slices across 8 pathologists, with a total of 10 hours of inspection. And then we develop a YOLO classifier to detect the region of interest that pathologists will typically interested in. After we get a region of interest, we will use the frontier vision language model to help us distinguish whether it is benign or malignant. On our internal validation data set, we can actually achieve surprisingly 100% recall on detecting the lymph node metastasis. Oh, well, of course, this task is not super difficult, but 100% recall suggesting that you can truly rely on such AI to give you an initial assessment. And additionally, we further perform actional validation on the Sweden data set. We found that our model can still reach very high performance on 97% of the recall. And the core recipe, because our pathology O3 model is also using the Gemini or GPT-03 to give us the final assessment. Our core recipe is that we train a YOLO detector based on pathologist behavior to locate actually useful, helpful region of interest. We locate the region of interest is much better than any other model. That's our core recipe. And by doing so, we are now collecting even more exciting data. We are right now using a near-infrared illumination commercial-grade eye-tracking device to track the user behavior, not only the mouse movement and viewport activity, but also the actual eye gaze. And now, when pathologists are making a diagnosis, we encourage them to say something when they see something. So then we will be able to get a bunch of very useful image and text pairs after the post-processing. And that data collection efficiency is very high. We can actually get 6 image and text pairs in a minute. So think about that. In the past, when we try to collect image text pairs, it is very slow, very tedious. Pathology, they have to carefully annotate proper region of interest and type down their comments. Now, with this automatic collection, you just need to talk to the system. Then you can build the same scale of the data set within 30 business days. And then you can train your own customized foundation model for working and signing out your own cases. We believe in the future, with such set of data collection, you'll be able to have your own customized AI copilot to helping you to make sign-out cases and make the diagnosis more accurate. Okay, so we have discussed the pathologist, the importance of pathologists when making the clinical diagnosis, and we have also covered the huge problem, the challenge of making an accurate clinical diagnosis. And our solution for diagnosis challenge on cell level is the nuclear I/O platform, and on the tissue level, we propose different type of foundation models, such as PLIP for image patch analysis, MelanDX for knowledge-enhanced vision language model, and VistaPath for image segmentation. And we also cover that to train a powerful AI model, we need to collect data at scale. And we oftentimes we reach the data limitation. And our solution is to collect regional interest data through pathology chain of thought behavior, as well as the eye tracking system. But having all those advancements, our question is, how do we deploy these AI tools to actually benefit our clinical diagnosis workflow, right? And where to perform such active learning and eye tracking experiments, where to collect such data, how to use these tools to accelerate the scientific discovery, and most importantly, where to invest the science in long term. Well, our solution is TissueLab, a co-evolving agentic AI ecosystem that can help you to run AI agent workflow to solve questions and clinical tasks. So every time when we talk about agentic AI system, what exactly those agentic AI systems are? Well, you can think about Lego blocks. AI tools are like Lego blocks. We have segmentation model, we have detection model, we have VistaPath, we have all different kind of tools. And large language model will help us to assemble those tools, the same amount of tools, to different functional workflow or different functional machine to solve the actual problems. And so that's the power of agentic AI system driven by large language model. So our system is pretty straightforward. We can run AI agent workflow to solve any research question and clinical task. You can just simply ask a question like, help me to calculate the ratio of tumor versus lymphocytes in this breast cancer tissue. So then we will select the most appropriate AI tools in our model factory and arrange them into a final workflow. We will not only generating you the final workflow, but we also help you to run the final workflow and write the Python code to help you to analyze the result. And finally, our summary agent will provide you the final answer. For example, in this case, the ratio of tumor to lymphocytes within this region is 1.53. And now you can just type into, you can just ask the question in our conversational chatbot, and we will generate the workflow for you immediately. So speaking about the powerfulness and the beauty of agentic AI, why we want to introduce agentic AI? Why this is better than foundation model? Well, I'm not going to say this is better than foundation model. Why this is a very nice thing on top of the foundation model? Well, think about that. We have over 8,000 different diseases, and every single disease we may have 20 different tasks to solve. So there are basically infinite number of tasks to solve. And speaking about such high over and under diagnosis rate and insufficient understanding, even within the skin cancer, within the melanocytic neoplasm, we have 44 different subtypes. The current solution, either task-specific model, can only solve one problem at a time. And pathology foundation model with fine-tuning can potentially solve all the problems, but it is underperformed on the rare diseases, and especially those diseases with limited training data. And most importantly, both task-specific model and foundation model just return you yes or no with limited transparency and explainability. And most importantly, it seems to be that AI models are trying to replace you, not assisting you, which is very problematic. We don't want AI to replace us. We want AI to assist us, providing us the reasoning trace and helping us to make the diagnosis rather than just replacing us, right? So our agentic solution for machine learning it will be the solution. Our solution is pretty much the same as the backpropagation of a neural network. Well, think about backpropagation. Think about neural network. We have an input. We put the input. We send the input to the neural, and we have a different connection, weight and bias, and we finally generate prediction. We compare the ground truth and get a loss, and use the backpropagation to minimize the loss. And then we will fine tune and change the weight and bias over the time, over the iteration. The same analogy applies to our agentic design. Our input is the same, but every single neuron is now replaced by every single model or every single AI tools. We still generate the output, we still generate the prediction, but comparing to the ground truth, our loss is no longer to be the computational numerical loss. It is the loss described by the language model. The language model will tell us whether this current arrangement between those model connection will be the potential ideal solution. And the system will try to iterate and try to find the best potential combination to make the model work and minimize the final loss. And that's our agentic AI solution. So just like a gradient descent for minimizing the objective function, we starting from the starting point, every single step, we try to find the most ideal location, steepest descent direction, and move to the next point. Through the iteration, we'll be able to eventually find the local minima, which is the right model combination to solve the problem. Here's an example to illustrate that idea. Tubular and glandular formation and tubular glandular grade in breast cancer. These are all the three different scores for the breast cancer tubular glandular formation. But those with a low score indicating those tumor cells are forming a ring structure. They have a lumen inside. And the second score, the ring structure will become less and more. There will be more cluster of the tumor. And when we have a high score, there will be basically no glandular formation of the tubular formation. There will be all cluster of the tumor everywhere. So to solve this problem, we use our tissue lab agent evolving trajectory ability to every single iteration. We will try to find the model combination, and at the very end, we will find the best model combination to solve this problem. Given the same amount of training data, we found that our tissue lab solution is much better than the pathology, even the best pathology foundation model, given the same amount of training data, and is also much better than a manual workflow, highlighting this evolution of the agentic AI is the right way to solve the problem. And most importantly, we provide the transparency. Every single result, you can visualize it on our system, so you can audit it and understand whether the model is performing accurately or not. Right now, Tissue Lab is fully functional with multiple validated models, and right now we have received over 6,000 users worldwide. And most importantly, our Tissue Lab is an ecosystem now fully compatible with the eye tracking device. So in the future, we're aiming to deploy the Tissue Lab and invite pathologists to make a diagnosis in our platform. And we are also going to collect their behavior data and hopefully train a much better AI model that can truly assisting pathologists to improve the diagnosis, as well as finding new scientific biomarkers, interesting, meaningful biomarkers. So to end this presentation, I would like to take analogy of the investment of large language model. It is the endless help and data curation from Google and Quora, and that's how we are able to build a powerful ChatGPT to help back for us, to helping us to on a lot of things. I think the investment of future science is pretty much the same. We need to collect public internet knowledge. We need to curate the public internet knowledge. We need to collect expert annotation, shadow with experts, and to teach the AI in a proper AI platform. And finally, we need to learn those tacit behavior and chain of thought insights from the real pathologists. And then that's the potential and that's the opportunity for us to develop a next generation precision medicine and AI co-scientist. And that's our long-term goal. With that, I would like to thank to all my students and postdocs for this fantastic work, and thank you to all my collaborators. And thank you very much. Happy to take any questions.
Thank you so much. That was fantastic. That was amazing amount of work that you're leading. This is really, really good work. So as I said, like I think if anybody has any question, they can raise their hand, or you can also put it in the chat. I can read to it. But I'm going to start with one question, Mzi. I think it was pretty interesting to see some of the work that you're using as the models of analogy of learning tennis from those human motion data, and then you're applying in this. But how do you ensure that the behavioral signal that you're capturing, such as like the mouse movement, zoom, and I think eye gazing aspect as well, actually encodes to like diagnostic reasoning rather than just like attention or a habit of a pathologist could be? How do you differentiate and curate that?
That is a fantastic question. So the question is basically, how do we ensure the quality of the behavior data produced by the experts? That is indeed quite challenging, because often the time when pathology are making the diagnosis, they're not always looking to the pathology-related lesion. Sometimes they are also interested in very interesting, funky shape of the whole cell image, and they will typically spend more time on it to just exploring the potential. So we believe the solution is not easy, and our current solution is to invite them to say something when they see something, so that we can get a real transcription to understand what exactly they are looking at. Is that really diagnosis relevant or not? And secondly, even with their every time when they are talking about something, their eyes are often the time just floating around. And that is also very, very difficult to ensure that that eye tracking data is is aligned with our real practice. Our solution is we actually develop a very sophisticated pipeline to pre-process those behavior dots and trying to smooth them and ensure these behavior are much more cleaned. Yes, so that's our two different approaches.
I see. So you're kind of also thinking of reinforcement learning as a feature to kind of improve your model prediction with that. Yeah, I think that kind of makes sense.
Exactly.
I'll read a couple of questions from the chat as well. We have one is for clinician who manages diseases where tissue pathology is important, what practical steps would you recommend for them to explore potential research collaboration, AI, digital pathology research?
Yeah, that's a great question. Who manage disease where tissue practical steps to explore potential research collaboration? Well, I think the bottleneck often the time is the data and the question. So sometimes clinicians are interested in like disease relevant or outcome related question. Sometimes pathologists are more interested in the morphology, linking the morphology and diagnosis. It's all about defining the right question and using the right data, and um, to propose the right solution. And that is actually the powerfulness of agentic AI system. When you have questions you want to answer, you can definitely ask us or a senior students who help you to develop a computational workflow. But agentic AI can potentially help you to design it by learning our strategy as well. Hopefully that answers your question.
I think so. All right. So next comment is amazing work. Does Tissue Lab Agent AI Agentic Toolbox plan to include omic data as a multimodal approach, molecular data plus morphology, or triage for cases where molecular data is required for difficult to diagnose tumor?
That is a fantastic question. So when we roll out the Tissue Lab platform in our preprint, our title is actually a co-evolving agentic AI system for medical image analysis. We are not limited to pathology histology images. We are also able to process spatial omics data, including spatial transcriptomics and spatial proteomics. Some functions may not be readily available on our online platform, but our agentic AI are able to expand the ability on those data. For example, like if we are trying to identify the like T cell for example, if we want to explore the relationship between the T cell and tumor, and how does that correlate to the response or outcome, it is relatively easy to flag out the tumor cell, and it's relatively easy to train a model to classify tumor cell in the histology, but it's relatively difficult to classify T cell in the histology. When we have a paired spatial proteomics data, it will be able to flag out the CD8 or other different markers, and then we'll be able to better tell the T cell. So combining different data modality will definitely help a lot. And our tissue agentic AI system are able to handle such complex question, as long as we have well-documented and well-documented AI tool in our model factory, then we're able to do that. Yes.
That makes sense. Well, I have one more question. I think it's fantastic to see that you already have like 6,000 users for your platform, Tissue Lab. I wonder that's really you're looking at like real world example that's outside of like pen system as well. Do you see any common failure modes in that usage and what those are? I'm just curious.
Yeah, many times. We receive a lot of feedback from all different users, scientists across the world, as well as a lot of different pharma companies. They also using our platform a lot. And most common questions they're asking is, so often the time they just realize the AI tool are not perfect, and that's actually very problematic. Like if even if your large language model driven agentic AI design is 100% accurate, but the model performance is also often the time largely limited by the actual tool accuracy. It's bottlenecked by that.
Yeah.
And that's the reason why we believe that active learning could be the potential solution to whenever you see the tool is imperfect, we want to make your the model be more interactive so you can fine tune it on the fly. And that's part of the reason why we roll out this interactive foundation model for pathology segmentation, because we want the user to improve the tool on the fly to solve the actual problems.
Okay, yeah, that makes sense. All right, we have 1 minute. Maybe I'll quickly see the last question. One from Yan Pan. I'm wondering if you are basically using label data for agent AI training or based on unsupervised learning. If the former case, how do you get so much label data?
Yeah, that's a perfect question. So when we are comparing our agentic AI solution versus the state-of-the-art pathology foundation model, we want to make sure the experiments are fair and comparable. So we do use the label data to train, and we don't use a lot of label data, but there are a lot of label data, to be honest, online. But in our experiment, we try to use as minimum data as possible, given the same few shot setting. Does the agent solution can be better than the foundation model solution? And that's our training strategy.
Sounds good. Well, thank you so much for joining today. This was a fantastic talk. We're now at 1 o'clock. Well, thank you everyone for joining, and I'd like to thank Dr. Huang for his fantastic presentation today.
Thank you so much.